This video is the supplement to the video on the implicit function theorem. In that video, we discussed and proved the implicit function theorem. In particular, in the proof, there was a point at which we discussed the invertibility of a block matrix of a certain form, and we asserted that it was invertible exactly when certain block components were invertible. And so here we are going to make that precise, and we're going to prove that statement that we asserted at that point. And hence we are titling this block matrix invertibility. So let's get into it. Now, by the context of that referenced video, we are going to be dealing with the special case of block matrix invertibility, where our block matrix is a 2x2 block matrix of this form here, where we have an upper triangular block matrix. So we have a block here, block here, block here, and this block is assumed to be zeros. Now, in fact, in the situation that we were concerned with, we actually had these two things reversed. That is, the zeros were here, and there was some other random stuff here. But it really won't matter at all, because when you take the transpose of a matrix, that isn't going to affect invertibility. But just because this is of an upper triangular block format, and we like upper more than lower, we'll just go with this format instead. So just to be clear, as follows, our matrix is going to be a matrix M of the form given here. It's a 2x2 block matrix where we have square blocks here, and then rectangular blocks here and here that fill in the rest. And in particular, this bottom block, this bottom left block, that is going to be all zeros. So just for example, you can see one such example here. So here is square submatrix, corresponding to this and this respectively, and then the b's, of course, are this, and the zeros are this. So the theorem that we asserted in that video and that we want to prove now is that if we suppose that A is invertible, that is, this block matrix here is invertible, then the overall matrix M is invertible if and only if C is invertible. So an alternative but equivalent way of stating this theorem would have been to say that this overall matrix is invertible exactly when the two blocks here are both invertible. So let's prove this theorem. We are not really going to give much motivation for the proof, but we will do the computational verification that this really is true, that what we've just asserted. And the way that we're going to prove that is that we are going to assert that this is the inverse matrix. So if this is the original matrix M, then this is the inverse. And notice that the inverse is going to be referencing the inverse of A and C. Okay, well, how can we test that claim that this matrix is the inverse? Well, what we do is we just multiply them together. So here is the matrix M, and here is what we are claiming to be M inverse. So we'll just put it in quotes for the time being, M inverse. Let's see if we actually get the identity when we multiply these two together. Well, if you know how a matrix multiplication works in block format, you know that you can just essentially treat these as if they were entries of a matrix, and you're just multiplying the blocks. So if we want to get the top left block of the resulting product, then what we do is we take this part times this part plus this part times this part, just as if you were treating them as entries of a matrix. And if you were to do so, then you see that you get A times A inverse plus B times 0. So here's the A times A inverse, and here's the B times 0. And then it's the analogous thing for all of the remaining blocks as well. So, so just for example, if we do this one here, you would be taking this first block row times this second block column, and you see that you get A times this thing and B times this thing, and that's exactly what you see over here. So filling all that in, this is the overall resulting matrix that you get. And you can notice that here, for example, you get A times A inverse is going to give you the identity, and then this part is going to give you 0. So you just have the identity here, so that's why you get identity matrix there. Similarly, down here, what's going to happen is this 0 and this will cancel to give you 0, and then this will give you identity again. So that gives you the identity here. And then analogously, these parts will give you zeros if you work out those multiplications and additions as well. So then in total, this resulting matrix is also going to be an identity matrix overall, because the individual blocks on the main diagonal themselves are identities, and the off-diagonal blocks are zeros. So we did it. We just multiplied m and what we claimed to be m inverse, and we did get the identity, so that must mean that this really is the inverse matrix. Now technically, you should also do the multiplication in the other order as well, so multiplying what we claim to be m inverse on the left. But I'll leave that detail to you if you want to go through and do that, but you'll get the identity matrix again, thus showing that this really is the inverse matrix. So this proves the statement because if we assume that A inverse and C inverse exist, then that means that this overall matrix exists and it's the inverse of this, so then the inverse of this total matrix exists. And then the other way around, if the inverse of this exists, well, it has to be this, but this is only defined when A and C inverse are defined. So that shows that the two statements are equivalent. So that's the short computational proof that we have for that theorem. Now just one extra note, just as we said in the beginning, the invertibility of the upper triangular block matrix is equivalent to the invertibility of a lower triangular block matrix. And again, that's just because taking the transpose doesn't affect invertibility. So if you were to take the transpose of this, you would get something of this format over here, and vice versa. So we've proven what we want for upper and lower 2x2 block triangular matrices. Now one more thing before we wrap this video up. Now this isn't at all necessary for the proof that we wanted to give, but this is just for your own edification if you want to explore this topic any further. And more generally, if instead of having zeros on one of the off-diagonal blocks, if instead we just had a truly general 2x2 block matrix where we just had 4 blocks where these parts were square, then if we wanted to discuss the invertibility of this matrix, then what we do is we consider something called the Schur complement of one of these blocks. So specifically, if we're talking about the block here, which is A, then the Schur complement of A is S sub A. That is defined to be this quantity here. So you take this block and then you subtract this times this inverse times this. So you're just doing a clockwise motion like that. So again, that's the Schur complement for A. And then symmetrically, we could also be discussing this in terms of the Schur complement of D. So instead of dealing with the Schur complement of A, we could have done it with D instead, and that would be defined symmetrically, where we would have S sub D. The Schur complement of D is this, where you'd have A minus B times D inverse times C. So again, you're just doing a clockwise motion. Now, the point of defining this so-called Schur complement is that if we assume A is invertible, and again, you could do the same thing with D, it would be an analogous statement, but we'll just do it with A. So assuming A is invertible, then the overall matrix M is invertible exactly when the Schur complement of A is invertible. Now, we won't go through the proof of this, but it really is just a generalization of what we were discussing above. In particular, if we have a upper triangular block 2x2 matrix where this part is zeros, then if you think about what this Schur complement of A would become if this were zeros down here, then what would happen is this part, which is now zeros, would be over here, and so this overall product here would just zero out, and you'd just be left with D. So in the case where you have a block upper triangular or lower triangular 2x2 block matrix, then the Schur complement is just going to be the opposite main diagonal entry. So the Schur complement of A would be D, and symmetrically the Schur complement of D would be A. And again, that's going to hold whether the zeros were in the upper part of the matrix or the lower part of the matrix. So if you wanted to actually prove this statement, then you do a similar computation to what we did above. It would become more complicated because you'd be involving the Schur complement in here, but secretly the Schur complement is already showing up here. But anyways, you can explore that further if you are curious about it. But for the sake of the implicit function theorem proof, we have proven what we needed. So then this concludes the comprehensive proof of the implicit function theorem, technical details and all. Thank you for watching.